Learn like a pro.
Welcome to The Explainer. Today, we're going to take a journey from the invisible world of jiggling particles that make up everything, all the way to the temperature and energy that we can actually feel. So let's just dive right in.
Okay, let's kick things off with a fundamental question. You know, we use the words heat and temperature all the time, almost like they're the same thing. But in physics, nope. They are completely different. And honestly, getting this distinction right is the key to understanding everything else we're going to talk about.
So to really answer that question, we have to zoom way in. We need to look deep inside matter itself to understand the hidden engine that powers everything, from a freezing block of ice to a boiling cup of water. So I want you to imagine that any substance is just made of countless tiny particles, right? Let's just think of them as dots. Now, these dots aren't just sitting still, no way. They are constantly vibrating and moving around, and they're all held together by these invisible forces that we can picture as tiny little springs connecting all the dots.
Okay, so the total energy that's locked up in this whole system of dots and springs is what we call internal energy. And it's really made of two parts. First, you've got kinetic energy. That's the energy from all the motion, all the jiggling. And second, you have potential energy, which is the energy stored up in those spring-like forces. And trust me, understanding this split is super important, because as you're about to see, temperature only cares about one of them.
So now that we have this picture of what's happening on a microscopic level, let's connect it back to something we can actually measure with, a thermometer.
And here it is. This is the crucial distinction. Temperature does not measure the total internal energy of something. It's way more specific than that. It only measures the average kinetic energy of the particles. So, in simple terms, temperature is really just a number telling us how fast, on average, all those tiny particles are moving.
You can think of a thermometer as being like a kinetic gauge. When you add energy and the particles start to move faster, their average kinetic energy goes up, and that gauge, which we call temperature, goes up too. When they slow down, the reading goes down. It's that simple. It's a direct measurement of all that microscopic motion.
So if temperature is only tied to kinetic energy, it begs the question, right? What happens when we add heat, but it affects the potential energy instead? I mean, where does that energy go if it's not raising the temperature?
Well, this is where that added heat energy hits a fork in the road. It has two possible destinies inside the material, and it can only follow one of these paths at a time.
All right, so path number one, the energy goes straight into the particles' kinetic energy. It just makes them move faster, and what we see is a change in temperature. This whole process is governed by something we call heat capacity. Path number two is different. Here, the energy is used to fight against those little springs between the particles, targeting the potential energy to pull them apart. This is what causes a change of state, like ice melting into water. And get this, there's no change in temperature at all while it's happening. That hidden energy doing the work is called latent heat.
Okay, let's just focus on that first path for a minute, the one that changes temperature. What's so cool here is that different materials respond to heat in completely different ways.
This unique property is called specific heat capacity, and we usually just call it lowercase c. You can think of it like a unique thermal fingerprint for every material out there. It tells us exactly how much energy you need to raise the temperature of 1 kilogram of a substance by just 1 degree. This is exactly why a metal spoon gets super hot in your tea way faster than the ceramic mug does.
And what's really interesting is just how different these fingerprints can be. I mean, look at this. To raise the temperature of 1 kilogram of water by 1 degree, you need 4,200 joules of energy. A joule is just our unit for energy, by the way. But for the same amount of glass, you only need 700 joules. That is a massive 6-fold difference.
And this right here shows you the real-world effect of that difference perfectly. A substance like water, which has a high C value, that's curve A, it cools down really slowly because it has to release a ton of energy for its temperature to drop. But a substance like glass, with its low C value, that's curve B, it cools down super fast.
So the really crucial takeaway here is that materials with a high specific heat capacity, like water, act as an energy buffer. They are just really resistant to temperature changes. And this isn't just some abstract idea. This is precisely why coastal cities have moderate climates, while inland deserts have these extreme temperature swings. The ocean is literally acting as our planet's thermostat.
Okay, let's move on and see how we can actually put all these principles into action. We can use this knowledge to predict exactly what happens when hot and cold objects get mixed together. This whole process is governed by one of the most fundamental laws in all of physics, the principle of conservation of energy. All it means is that energy can't just be created or destroyed, it just moves around. In our case, heat energy simply flows from the hotter object to the colder one until they find a balance.
And we call this balance point thermal equilibrium. This scale illustrates it perfectly. The amount of heat energy lost by the hot object is perfectly equal to the amount of heat energy gained by the cold one. They eventually meet at some final, stable, in-between temperature.
So let's try to solve a real problem with this. Say we have a hot 600-gram aluminum sphere, but we don't know its initial temperature. We drop it into 3 kilograms of water that's at 30 degrees Celsius. After a bit, everything settles down to a final temperature of 50 degrees. So the question is, how hot was that sphere to begin with?
We can totally solve this puzzle step by step. First up, let's calculate the energy the water gained. We know its mass, its specific heat capacity, and its temperature change. That all comes out to 252,000 joules. Now, because energy lost equals energy gained, we know the aluminum sphere must have lost that exact same amount. So we just set up the energy loss equation for the sphere and solve for that unknown initial temperature, which we'll just call T.
And when you do the math, boom, the answer is revealed. The sphere's initial temperature had to be 517 degrees Celsius. It's just amazing how we can use our understanding of vibrating atoms to calculate a concrete, real-world number like this.
This whole journey, from microscopic particles all the way to a macroscopic calculation, really shows how understanding these fundamental properties of matter lets us explain the world around us. Which kind of leaves us with one last big thought to think about. Given water's crucial role as a thermal buffer, how profoundly different would our planet, and maybe even life itself, be if water didn't have such a uniquely high specific heat capacity?